Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. We will continue with the topic of mechanical properties of materials. In last session we discussed how to measure the stress and strains. Now we will discuss the stress-strain relationship using Hooke's law. For the application of Hooke's law, we have some assumptions. Let's say the chemical composition of the material is constant throughout. We may have some imperfection in the material because of the manufacturing processes, but we assume that the chemical composition is same for the entire material or the specimen. Then there is no change in temperature during loading, as we have seen that how significantly the microstructure is affected by the temperature. So we assume that during loading the temperature remains same. Then there is no stress concentrations and the specimen of the material is of prismatic cross section. Means if we have a specimen, then we assume that the cross section area is same all along the length of the specimen. But if we go for the microscopic analysis of the surface of the specimen, we observe some waviness on the surface of the specimen. So because of these waviness, let's say at this location the cross section area is minimum, and if we calculate using the expression of stress by sigma p over a, and if we use a minimum, here we will get the maximum or the higher stress value. So the stress concentrations are there in the specimen. So we assume that the surface is perfectly smooth for that very specific specimen of the material. Now further, the material is deformable because the Hooke's law is applicable for the material which is deformable. Now using these assumptions, the Hooke's law states that stress is proportional to strain. Considering different stresses, we have discuss the different stresses like normal stress, So sigma is proportional to the epsilon. If you take the example of the shear stress, tau is proportional to gamma. By removing the proportionalities, we will get constants in the expression. So sigma is equal to E epsilon. Now this E is the modulus of elasticity, or Young's modulus. And for this case, the shear stresses, we have tau is equal to G gamma. Here G is the modulus of rigidity. Now we also know that the strains are the mere of the deformation of the material, which can be made by observation using instruments or different gadgets, but the stresses cannot be measured by using instruments or gadgets, because these are the internal resistive forces of the material. Now then the stresses are calculated using constitutive equations or compatibility equations. Here constitutive equations means by application of Hooke's law, and the compatibility equations means the mathematical expressions which depicts the actual situation. Now, as we say, the stress is a function of strain. Now, if we plot the stress strain relationship, then this plot is going to be known as stress strain diagram. As we have sigma is equal to E epsilon. Now comparing this with the equation of straight line, which is y is equal to mx plus c. Now plotting this equation of straight line, this is x, this is y. Now here c represents the intersection point which intersected the y-axis at C, and m is the gradient of the straight line or slope of the line. And comparing this equation with the stress strain, we say here sigma is compared with y, epsilon is with x, and this E is the gradient or the slope, and here C is the 0, means the line passes through the center or the origin of stress strain diagram. So if we draw a line on the stress strain curve, now this is going to be the gradient of slope of the stress strain, which is E, the modulus of elasticity. Now further, this relationship not holds good for the infinite loading. There is a limit. Up till that, this relationship holds good. So at that state, this relationship is applicable. The state is known as the limit of the proportionality. So we can define as the limit of nullity as a state up to which the material follows the Hooke's law, because this not holds good for the infinite loading. So up till that loading which is applicable, so that limit is known as the limit of proportionality. Now further, we say the sigma is equal to E epsilon, or we may say E is equal to sigma over epsilon. So since the units of strain is there is no unit of strains, so the units of modulus of elasticity would be the same as of the stress, which are Newton per meter square or the Pascal. And if we take the example of two materials, let's say A, B, A is having the modulus of elasticity that, let's say, 1 E1, and B is having the modulus of elasticity E2, and here we assume that the modulus of elasticity of material A is more than modulus of elasticity 2. So if we plot this on the stress strain diagram, and let's say the on the plot, this is the modulus of elasticity, that is E1 for the material A, and the modulus of elasticity for the material B is E2. This is for the case of material B2, and we assume that value of that at some value of stress, let's say this stress value is sigma 1, and we draw a horizontal line which cuts these straight lines. Now if we draw from this intersection, here we have the value of the strain for the case of material A, let's say this is E1, and from this intersection we have the value of the strain of this epsilon 2. Now this indicates that epsilon 1 is the strain in material A at stress sigma 1, and epsilon 2 is the strain value in material B at same stress of sigma 1. And if we assume that the we have not assumed, actually we are saying that sigma 1 is same, so sigma 1 is going to be P over A, and here we assume that A1 AA is equal to AB. The cross-sectional area of for material specification, the specimen A is same of the cross-section area that is of specimen of our material B, and same is the loading for A and same is the loading for B. So it means for both the strains we have different values for both the materials, and here we observe that this strain 2 is more than epsilon 1. So it means the material having higher modulus of elasticity would have the low value of strain, less deformation. It means the material which is having more modulus of elasticity poses more resistance for the case of deformation, so it has more stiffness. So with this, the Young's modulus, basically the Young's modulus is the measure of the stiffness. More the higher the value of Young's modulus, it means more the material is stiff. Further, we say the Young's modulus that sigma is equal to E epsilon, and if we write this as P over A is equal to E del L over L, and if we assume the del L is equal to L, so this will cancel out and we will have the value of E is equal to P over A, which is equal to the stress, which indicates that if whatsoever is the length of the material of that very specimen, if the double is the, if we apply the modulus of elasticity, the stress of that value of modulus of elasticity, there will be double of the length of that very specimen. In other ways, let's say if L initial length of the material, that is 10 millimeter, and after application of same stress as the value of this modulus of elasticity as Young's modulus, the del L is going to be the 10 millimeter. So the total length is going to be 20 millimeter. So the Young's modulus actually has double the application of the stress of Young's modulus, double the length of that very specimen of the material. So we can define as the Young's modulus, the Young's modulus E is the value of the stress which can double the length of the the length of the specimen. With this we end our discussion here. Allah Hafiz.